Well, hello students, and here we are looking at vertical accelerated motion, and we're going to be looking at quantitative examples. So we're going to do some number crunching, and as usual, while you're watching these lectures with the PowerPoint, you will be taking notes, you will have your calculator out, and you will be working these problems before I show you the solution. So you want to get practice yourself, because whenever you have to do the problems, you want to make sure that you've gone through all the steps, figuring it out, how to put in the numbers, rearranging variables, so you can get this done on your own. So nothing like practicing a skill yourself, which you'll need to do. So please ensure that you are taking notes and you have your calculator and your pencil and eraser in front of you. So anyways, let's take a look at these equations. I refer to them as the star equations, and this is just letting you know on the AP Physics 1 formula sheet or equation sheet, we have all the equations that you're going to get on all my tests and on the AP test. And so I call these the 3-star equations. This is star equation 1, star equation 2, and star equation 3. And that's not because 1 is better than 3 or 2 is better than 1. Anything like that. It has more to do with the fact that this one's listed first, this one's listed second on the formula sheet, and this one's listed third. So you know which equation I'm talking about when I say star equation 1, when I say star equation 2, or star equation 3. Now I want you to notice that this is what they look like on the equation sheet. And since this has an X in here, you'll more associate this with horizontal acceleration. However, you'll also use these for vertical acceleration. So you have to know and be keenly aware that the X will turn into a Y because it's a vertical problem. And you'll also be keenly aware that when we are solving vertical acceleration problems, that the acceleration in the Y direction will be the acceleration due to the force of gravity. If the person happens to be on Earth or whatever the object is, and we use negative 10 meters per second squared. For the Knight textbook, you'll use negative 9.8 meters per second squared because the answers in the back of the book and also the solutions online will have negative 9.8 meters per second squared as the acceleration in the Y direction for objects in free fall. So I've rewritten them here for you. It doesn't look like that on the equation sheet, but you are experienced students and you know acceleration in the air due to gravity is going to be negative 10 meters per second squared. And we can look here and see that I've changed all the X's to Y's. So at the beginning of the year, whenever I had you write down information to memorize, these equations here were the two I said would be nice and quick for you if an object starts from rest or comes to rest, because it changes the star equations. Well, two of them, it changes significantly, makes it easy for us to just get to the point of what we're looking for. So the D for displacement, this is a general sign that we could use for delta X or delta Y. So now that we're dealing with vertical problems, we're going to put a delta Y in for displacement. And for acceleration, since the acceleration is in the Y dimension, we're going to use the value of G, which is 10 meters per second squared. And since it's heading down, we'll use negative 10 meters per second squared. So this is what these equations look like over here for vertical problems. So you want to look at this and make sure you feel comfortable with that. If not, memorize it until you get used to it. So let's go to the next slide. So you want to write down this problem and you want to start trying to solve it yourself. You're going to hit pause, and if you need a hint, you can press play and it'll take you to the next slide, and I will be giving you hints on the next slide, and but not the final answer, just hints. So hit pause, Owen, start this problem yourself and see if you can pick the right star equation and pick out the information you need. So here is your tip. Use star equation 3. You can use it as it's written, v squared equals v naught squared plus 2a delta x. You'll change the a to g, and you'll change the delta x to delta y. Or you may choose to use the simplified equation d equals v squared over 2a. Since the ball is dropped from rest, please use negative 10 meters per second squared for acceleration in the y direction. You can hit pause, solve the problem, get the final answer, box it, and then as soon as you hit play, you'll see the solution on the next slide. So here we are dropping the tennis ball, and since the problems that we set up start at this particular one, we're going to start at the origin of our coordinate system. So the initial y position is 0 meters. The final y position is negative 2.5 meters because it is being dropped and heading down. So this is my sketch. I know the initial velocity is 0 meters per second because it's dropped. It tells us dropped right here. And we're going to use the magnitude for gravity, 10 meters per second squared. So let's go ahead and take a look at our equation here. I'm going to use equation number 3 and not the shortened version, d equals v squared over 2a. Either one would work because since it's dropped. But I'm going to go ahead and just write this in its entirety here. So I do some algebra. We always rearrange the variables before we start inserting the numbers. And so I have the square root of 0 minus 2. And the minus is for the 10 meters per second squared because the acceleration due to gravity, even though this is the magnitude, we know that acceleration due to gravity is heading down towards the center of the earth, so we have to put a negative sign. If you put the negative sign in front of the 10, that gets the same job done. It doesn't matter either way. Over here, delta y is final minus initial. You notice I've done the work down here. Final minus initial is negative 2.5 minus 0 meters. So my delta y is negative 2.5, and I will take the square root of that. I want you to notice you're going to, since it's under a square root or radical, you're going to get a number, a magnitude. And for this particular equation, you are going to have to write the correct sign on the velocity by looking back at the problem. So it says, what's the final speed of a ball dropped from this height? It's asking you, what's the final speed right before it hits the ground? A lot of kids make the mistake of saying, gosh, it hits the ground, and guess what? It's sitting there. The speed's 0 while it's sitting there. It's not asking that. So you have to get used to the fact that they're not going to say right before it hits the ground. Some problems do, and I really like when it says that because that's specific and you know exactly what they're talking about. But they're asking for the final speed of the ball right before it hits the ground. So if the ball is heading down, you know the velocity is negative because in this course negative is down. So you're going to have to put the negative sign on there yourself to ensure the answer is correct. Go ahead and try this problem and hit pause, try it yourself, and then you can see the solution on the next page. So here's Spud Webb, and so it's looking for the initial velocity. So we take the fact that we know the final velocity at the top of the flight is 0. Acceleration for anything in the air, projectile, free fall, is always, if it's on Earth, is going to be negative 10 meters per second squared. So I have my third star equation. I know I am solving for initial velocity, so I've done the algebra here, switching the variables around. And I have taken the square root of this side so I can get the initial velocity. I put 0 in for final velocity. I put negative 10 meters per second squared in for the acceleration due to gravity. And then 1.1 meter is in the positive direction because we start the problem at the origin. So this would be 0. That would be your initial x position, your final, initial y position, and then your final y position is up here at 1.1. So it's a positive 1.1 for your displacement in the y direction. So your final answer is 4.7 meters per second, and notice that it's positive. All right, so football player, I'm going to give you the tip on this one. This particular problem, it's telling us has a hang time of 5.2 seconds. That means half the time is up and half the time is down. So 2 seconds up, 2.6 seconds down. So we're going to use this piece. We also know that 0 meters per second is the velocity at the top of the ball. Having that information is going to prove very helpful. And then we're going to use our 10 meters per second squared and for the gravity or for the acceleration in the y direction, we'll put a negative sign in front of it. So let's see how this goes. You go ahead and solve this first. Solve the second problem first with what speed did it leave the kicker's foot, and then second you're going to solve what was the greatest height reached by the ball. So you want to hit the pause button, go to the next slide to see with what speed did it leave the kicker's foot. And here is the answer. So you may want to pause it to see how the problem was worked out so you get the initial velocity as it left the kicker's foot. And now you could use that information for the greatest height reached by the ball. You'll have to use another one of those star equations to figure this one out. This one I used star equation 1. So I ended up using this one, the one that's time independent, meaning it doesn't have time in it. So your VF squared equals VI squared plus 2G delta Y. And I'll have the information that I need. This is the initial velocity. It left the kicker's foot. And 2 times acceleration in the y direction, negative 10 meters per second squared. So the maximum height is 33.8. So on the next slide, I actually use the second star equation. I plug in the same information to see if that would have worked it well as well. So if you want to pause and practice it yourself, that's fine. And here it is. Let's try this one. The delta y equals y naught plus vy naught t plus 1/2 gt squared. And here are all my inputs. I put them in, and sure enough, it works. So we get the same answer as we should. All right, this next problem here, I'm going to have you give this a try yourself. You're going to have to break it up into multiple pieces. So when you are ready to see how I attack the problem, we'll hit pause on the video, and then when you're ready to move on, hit play. But you want to draw a picture, pick the variables out yourself, and give this one a roll. So you can see here that I've dealt with the first part of the problem. How fast are they moving at the end of the speeding up phase? So since they drop, the initial velocity is 0 meters per second, and here's the time, I use this first star equation, VF equals VI plus GT, and I get the final velocity from the speeding up phase. And notice there's a negative sign. They are heading down. The next slide I have come to rest, so that means the final velocity is 0. So you have the initial velocity from the first part of the phase, and now they have to be braking. And you're like, yes, they must slow down, otherwise they'll blow through the concrete, and that's no fun when you go to a park and then the giant drop doesn't actually stop at the end. So please take a look at the acceleration that I've solved for here. It's quite a bit of acceleration in the positive direction to slow these people down. Hit pause, and when you're ready to move on, hit play. And so here is the last part. So it says, given these numbers, what's the minimum possible height of the tower? So I've broken this into two parts. This is the delta y for the speeding up phase, because you have to take it from the beginning. This is the displacement heading down while they were speeding up. This was the displacement while they were slowing down. And I added these two numbers together, so this ended up being the final answer. You can't put 46.9 meters as the 46.9 meters as a final answer. So you have to round it up because you need a little space to stop. So you round it up. Take a moment, pause this, take a look at the work, and try it yourself first. See if you can get to the answer on your own using some of the tips in here. Last one, pole vaulter. I'm just going to have you hit pause, and whenever you're ready, you are going to check the answer. So take a look at how this is set up. Take your time. So this takes you through the problem solving strategy. You saw me do this on the problems. Draw a picture, collect information. That's getting your variables settled. get your star equation ready, and then you rearrange your variables and put the unknown on the left-hand side, and then you put in your the variables that are known, and you do your algebra, and you come up with the final answer, and you ask yourself, does it seem reasonable? And if it's heading down, did you have a negative sign on your velocity? Or so you have to pay attention to those details because they make a difference. And here is a last picture. This is a sketch. This is a motion diagram, the point particle, and graphical representation, and a list of values. So this is something you're very familiar with, and you're responsible for knowing how to draw a motion diagram. It always helps to do a sketch, and you know how to read a xt or yt, vt, and at graph, and you always want to list your variables as well.